Welcome to the HC Insider Podcast, a podcast dedicated to the commodities sector and the people within it. I'm your host, Paul Chapman. Today, we're talking titanium. Titanium should play a crucial role in the future economy and energy transition. It has remarkable properties, not least how light it is compared to its strength, and how corrosive resistant it can be. However, the cost of manufacturing and the environmental impact, largely hidden, has relegated its uses to defense, the space race, and some high-end supercars. Titanium is also a critical metal, and yet is almost entirely manufactured in the West's geopolitical rivals. What's the market for titanium? How is it processed? What's its challenges? And are there solutions to lowering the cost and the environmental impact in manufacturing it that could unlock titanium and unleash its importance in the energy transition? Our guest is co-founder and CEO of IperionX, a titanium manufacturer, Anastasios Arima. Anastasios has had a 15-year career in the metals and minerals sector. As always, you can really support the show by leaving a positive review on the platform you're listening on. It really juices up those algorithms and helps expand the audience. I also want to take the opportunity just to note, as we're coming towards the end of the year, HC Group offers clients an array of advisory products, particularly around compensation, both trends and structures. If you have interest in engaging us on discussing these products, you can reach us via our website, www.hcgroup.global. That being said, as always, I hope you enjoy the episode. Taso, welcome to the show.
Hi, how you going, Paul?
We are talking titanium and those special qualities that make titanium both a very useful metal across multiple industries, but also key to energy transition. Before we dig into some of the challenges that poses and why it's not abundant and prevalent everywhere, can we get into the chemistry and understand what titanium is and what makes it so special?
Yeah, absolutely. Yeah, and I appreciate you inviting me on the show. It's great to be able to talk about titanium and what we're looking to do. So titanium is a bit of a holy grail of metals, a wonder metal, so to speak. It's lightweight, it's strong, and it's corrosion resistant, and often it's alloyed with other metals like aluminum and vanadium to impart certain properties to it. Titanium and its alloys are very effective in a lot of applications, and they can be a direct substitute for stainless steel and aluminum products that you see today.
Lightweight, strong, so replaces, as you mentioned, a lot of the stainless steels. It also has this amazing quality that it's not only corrosion resistant, but corrosion resistant to salt water.
Yes, absolutely. So its corrosion resistance is, if you put titanium in salt water, it would never corrode, whereas even stainless steel in salt water after 5 years, it would corrode. And if you put normal carbon steel in salt water, it would corrode. So it's used extensively in military applications in the Navy because of that. And it's used in a lot of power plants and industrial applications as well because of its corrosion resistance. It's actually used a lot in the electrolyzers for the hydrogen industry as well because of that corrosion resistance that it has.
So just get us all on the same page. How much stronger is titanium than steel?
It's a really good question. So if you look at commercially pure titanium, you would have sort of the strength of typical steels, but it would be 45% lighter. But when you look at the typical and the most common form of titanium, which is titanium alloyed with 6% vanadium, 4% aluminum, you have strengths. Our titanium typical strength would be 3 times as strong as stainless steel for 45% weight. So that gives you an idea. A lot of people think commercially pure titanium when you just say titanium. When we say titanium and its alloys. And there's some specific alloys which can be even higher, maybe 5-6 times that of typical stainless steel. So significantly stronger whilst being almost half the weight.
Yeah. I keep thinking of Lieutenant Dan's leg for those film buffs, but we'll leave that there. Okay. So okay, so it is this powerful combination of both lightweight and strong, and then also being corrosion resistant. Are there any other metals out there that compete with it with these attributes?
Not with the attributes of having that strength, having that lightweight, and having that corrosion resistance. It's also very biocompatible. So there's no real metals out there which has that. There's, of course, metals that have good corrosion resistance and might have good strength, but they're very heavy. Or there's some metals which could be stronger, some alloy combinations of metals, ultra high strength steels, which could be stronger, but they're much more heavy and don't have the corrosion resistance. Titanium has those unique attributes of being strong, lightweight, corrosion resistant. And so when you look at a lot of our applications today and the way we're going in the world where we want to have longer lasting products, we want to have products that are also more energy efficient, especially electric vehicles. We want them to be lighter so that we extend range for the same amount of batteries. There's not a lot of materials out there that can compete on that front, like the titanium and the titanium alloys that could be used in those applications.
Yeah. And the fundamental issue at the moment is cost, and we're going to dig into why that is. But staying on applications, so you've mentioned a few, but can you just sort of give us the broad buckets of where titanium is used? And I think that's indicative of how cost is really impacting its more widespread use.
Yes, absolutely. So we'll talk about costs later, but because of titanium's high cost in the current manufacturing process, the properties that we talked about are limited. You could use it everywhere, but you don't. But where we do use it is where cost is less of an issue. So you look at the aerospace industry. They try to use a lot of titanium there. There is a significant use of titanium in the aerospace industry. It's the largest part of the market. If you look at the defense industry, you have uses there for titanium where they need that strength and that lightweight. And then you look at some of those industrial applications where you have those extreme corrosive environments, but they need the strength. They need the heat resistance as well. And so it's limited to applications where extreme environments or extreme loads are going to be placed on it. On the metal, and so titanium is the only choice. If you look at the burgeoning space industry, there's a significant amount of use there as well.
Yeah, I mean, again, it's that sort of, where it has to be used for that combination of lightweight and strength. Right, okay, so let's get into the story about how titanium came to be discovered and how indeed it is mined and manufactured and processed into these useful alloys that you're discussing.
Yeah, absolutely. So titanium is a relatively young metal if you look at other metals out there. It was only discovered just a little over 200 years ago, but it was only commercially produced at commercial scale in the 1950s. So William Kroll invented a process to produce titanium metal, and then it was scaled by funding from the US government. It was the US Bureau of Mines back then in the 1950s to scale the production of titanium metal. And the reason that is that titanium metal is very hard. What gives it its corrosion resistance, which is the titanium, the oxide layer on top of the titanium, makes it also hard to refine the metal from a mineral. So in nature, titanium is found as an oxide. You have to get those oxygen atoms out of that titanium oxide. And so it's titanium dioxide. And so that was a very, very challenging operation to do that. This was a similar issue that aluminum had, only aluminum could go through an electrolysis process that was discovered in the late 1800s. Titanium is a level above. Its oxygen atoms want to bond to the titanium atoms even more. Then it's got a very much higher affinity for oxygen than, say, aluminum has. And so it's very hard to crack those oxygen atoms. So it was only done in the 1950s at the first commercial scale by William Kroll, but it was done in what is a very carbon, very energy intensive and very nasty environmental process, but that leads to very, very high costs. So that was scaled in the 1950s, scaled here in the United States, used for aerospace applications. Everybody's heard about the Blackbird, the SR-71 Blackbird. That was made all out of titanium, and the US military had and the CIA had a big program going on where they were sourcing titanium minerals from around the world from that. But then as we got into the last 30 or 40 years, there's been an increasing production of titanium from Russia, from China. And over the last 20 years, especially the Russian and Chinese supply chains have started to dominate a lot more. And what we have today is a situation where there's a lot of titanium industry is dominated by Russia. China is the largest producer of titanium, and the US now has no raw capacity to make the raw metal, what's called titanium metal sponge, which is the upstream part of the supply chain. And that refining process is very critical.
Yeah, and it's a story that's writ large across all of these critical metals, right? Where essentially a combination of Europe and the US wanting to outsource the pollution, and in this case, incredible pollution from the manufacturing process, and China in particular, but also Russia, willing to take that pollution on, but also dominate what is now a strategic supply chain. And it's fascinating, as you say, that so at the moment, only 15% is outside of China and Russia, in Kazakhstan, Ukraine, and Japan. And obviously, we'll come on to the market side, but Ukraine's, I assume, has dried up. Before we move into the markets itself, because I think it is instructive, can you just talk a little bit about that actual chemical process, the manufacturing supply chain to get it to usable titanium, and the sheer quantity of energy and nasty stuff that's involved?
Yeah, it's to get it to a raw metal, what's called a raw titanium metal sponge. It's very energy, carbon, and nasty process. But then to even take it from a sponge and make it a usable metal part is also very wasteful and energy intensive in the current industry. So you take titanium minerals out of the ground are quite abundant, sort of similar to lithium. It's actually quite abundant. It comes down to the processing, comes down to this refining. So you've got this abundant amount of titanium mineral in the ground. But then what you have to do to crack those oxygen atoms and create a purified titanium metal, it's not a simple reduction like what you have with say, iron ore, where you just throw it in with carbon and you create carbon dioxide and purified iron, and then you can go ahead and alloy it and make steel. In this case, that's not possible. Aluminum was similar. Aluminum, they then figured out they could apply electric current and create, again, carbon dioxide in the process and create purified aluminum metal. With titanium metal, that didn't work either. The oxygen atoms were just so attracted, it would just immediately pick up those oxygen atoms again, and you couldn't create a purified titanium metal. So the way to break those oxygen bonds and then create titanium metal was essentially a process to create an intermediate product called titanium tetrachloride. So you would take the titanium dioxide, you would still create carbon dioxide, it's a significant amount of carbon emissions, by throwing it in a chlorinator and pump it with chlorine and carbon and a lot of energy to get the reaction happening. That would then create carbon dioxide, and you'll be left with these titanium atoms floating around. They will have to attach to something, because if they didn't, they would attach back to the oxygen atoms in the atmosphere. So you would pump it with chlorine and they'll create titanium tetrachloride. Now that's a very nasty, corrosive chemical, but you can't do anything with it other than now you're able to reduce it with something to create a block of titanium metal easily. So you would pump it over into like a distillation process. A reaction in a reactor where you would react it first with molten magnesium metal, which is, again, very energy intensive and very dangerous as well. That's where a lot of the fires and explosions in these plants come in. It's in the molten magnesium metal. Sounds bad. It is really bad. And a reaction would happen where the magnesium would then take those chlorine atoms, create magnesium chloride, and you could deal with that. But then you'll be left over with purified titanium in that solution. This is the spongy reaction, form, isn't it? That's the spongy form after you've distilled out over many days the magnesium chloride in under a high temperature. So you'll then be left over with this spongy, cakey looking appearance of titanium metal. Now that happens in the reactor where you actually have to cut off the iron that the reactor essentially that happened in that. So you've got going from that sponge to then something that you can use, you lose already 10 to 20% of the titanium metal that you've put in there. And then from that sponge is a tradable It's a commodity, and that's what we bring into the United States now. But that's dominated by Russia, China today. But then you can't do anything with that sponge. It's a dendritic sort of material. You have to melt it. So you bring it in, you put it into a typically a vacuum arc remelting process where you melt it multiple times. That's where you can introduce a little bit of titanium metal scrap into that process. You pack it together, you weld these sponge and these titanium scrap pieces together, and you melt it down multiple times to get to a titanium metal ingot. Again, very long process, a very energy intensive process. But you create a big sort of 10-ton ingot. Now that 10-ton ingot is not usable. You then have to take that ingot, cut it up, extrude it, hot work it into what's called milled products. Now, in that process, each time you hot work the titanium metal, it's going to pick up oxygen. You want the oxide on the outside of the metal. You don't want it on the inside of the metal because it makes it brittle. So when you want to re-hot work it into, say, a bar or something like that, you always have to shave off that oxide layer before you re-hot work it, I guess. And in that whole process, you can end up having to a mill product another, 20, 30, 40% loss of titanium metal. So not only are you going through this very energy intensive process, very carbon intensive process, and long process that takes months, you also then have this significant amount of titanium metal scrap generation to just get to a mill product, which a customer can then buy and machine into a titanium metal product, which also creates a significant amount of waste. It sounds like a very long, intensive, costly process. It is. And that's what's kept titanium metal back to only be used in the most challenging of applications.
Okay, so can you help us understand, firstly, just volumes and scale? So how much spongiform is produced, and how much of that do you need to make how many ingots, or those 10-ton ingots are produced, and then what the market size is, and then be really instructed to understand kind of the pricing here as well?
Yeah, it's a good question. It's quite a complex and opaque market, but from a high level globally, we have about 350,000 tons of titanium metal sponge production a year. You would have a lot more if it was cheaper, but that's what it's limited to. Still a fairly large market. 50+% of it in China, 72, 73% odd in China and Russia together. What happens though is, for the US, for instance, you bring in and you use about, in round numbers, about 45 to 50,000 tons of titanium sponge. You then mix it with another 40,000 tons odd of titanium scrap, and you create about 90,000 tons, 80 to 90,000 tons per annum of titanium metal ingot. You then lose some of that ingot as you go into more bars and usable ingots, so you lose maybe 10,000 tons of that, and some of the numbers that we've seen. But then from that titanium metal ingot, we end up with mill products that are then sold to the Boeings of the world in this country of only like 20,000 tons per annum. There's a significant amount of scrap generated in the process to make those mill products. Since the Ukraine crisis and the Russian invasion of Ukraine, sponge has gone up in price. You're talking closer to $14 a kilogram from what was around $10 a kilogram, so $10,000 a ton. So already expensive. But when you look at a titanium metal ingot, which is tradable as well, you're looking, depending on if the ingot is alloyed or commercially pure, you're looking at over $20 a kilogram, approaching $30 a kilogram. But then when you look at those titanium mill products, on average, you're paying, $70,000, $80,000 a kilogram. So mill products can be anything from bar to wire to plate. We hear of bar being in the $65, $70 a kilo range, wire being $100 to $130 a kilogram range. So very expensive inputs, which they themselves are not parts. You then take, for instance, in the traditional process, you could take a plate and then you'll have to machine that plate out to make, say, a frame for a bulkhead or something like that for an aeroplane. So then you buy a plate for $70 a kilo, $70,000 a ton, but you'll only end up using maybe 20% of that when all is said and done as part of the airframe. The rest of it is scrap. And so very high cost to buy the product, then very high scrap generation to make your end part that you need to use, leads to a very high cost for that end product itself. It's a very inefficient, costly supply chain.
The HC Insider podcast is brought to you by HC Group, a retained search, intelligence and advisory firm focused solely on the global energy and commodity sector. With 6 locations across Asia, Europe and the Americas and over 50 consultants. To find out more, go to our website, hcgroup.global. There, you can also sign up for our HC Insider content for more interviews and white papers on relevant trends and talent impacts in the commodities world.
And from a market perspective, so you've mentioned, I guess, 3. There's the scrap piece that's traded, you've got the spongy form that's traded, and you've got the ingots that are traded. Who's doing that? How are these things traded? Is there a spot market? Is it all long-term contract? Can you just give us a sense of the players in this space?
It's similar to what the lithium space was like maybe 5-6 years ago. It's very opaque. It's very contract driven, but there is some markers in the industry. The scrap market, there's a range of players in the tradable scrap market. Not all the scrap is recyclable, whereas our process it can be, but traditionally not all the scrap is recyclable. Only 60% of it is probably seeing full circularity. That's quite internationally traded, but also traded quite a lot here in the United States to try and lower the cost of the manufacturing of the ingot. But then the sponge market is definitely dominated by Chinese for the lower grade stuff. The sponge market was dominated by Russia, but Russia took the initiative to make more of the downstream products and sell it to us. But then Japan trades that sponge extensively with the United States for remelting here in the United States. So there's a fairly large market there for the sponge.
So is titanium classified as one of those a critical metal? Where are we at from sort of when the supply chain is tied up? Is it sanctioned, for example? What's the political backdrop to titanium?
Yeah, so because of titanium is a critical material as defined in the list released by the USGS and the White House. So it is a critical metal. It is critical because of the use of it for national security. So we extensively use it in the military here in the United States. But it's also classified as a critical material for the Europeans because of their military and aerospace industry as well. It is sanctioned here in the United States, so we've stopped bringing in titanium metal. So Russia used to supply a lot of sponge to around the world, but then they took the initiative to not supply sponge, to supply more downstream products, those mill products. And they were shipping sort of 6,000 tons a year of critical components for the aerospace industry into the United States. And since the Ukraine crisis happened, that's been sanctioned. And so that's zero. And so the industry is scrambling to find new alternatives to develop those supply chains. Airbus actually helped to get titanium metal off the sanctioned list in Europe, which is, goes against the whole idea of why it should have sanctions. But there was just no alternative. You don't have titanium, Airbus doesn't have airplanes to produce.
Yeah.
So it is. I was the founder of a company called Piedmont Lithium, and so lithium is a huge thing today in electric vehicles and will be. It's really important. But from a national security perspective, we don't use a lot of lithium. There's a few battery packs for the warfighter where you use lithium, but it's not if we didn't have lithium, we would still have a military. You don't have titanium, you do not have a military, and you do not have an air force. And that's critical in today's world.
Fascinating. And do we see any of, you've been in the commodities industry for a long time-ish. Do you see, you mentioned lithium there, and we've covered lithium a few times. And it's interesting you say that, titanium sort of lithium 5 years ago from a market perspective. Because what we're seeing in lithium today is obviously a spot market in China. You're starting to see more and more the traditional metals traders trying to look at it. What's their role within the lithium market? It has many of the same attributes in terms of when we say lithium, are you meaning lithium hydroxide, whatever it might be, lithium carbonate? Long-winded question, but Are we seeing traditional commodity traders start to look at titanium? Have they looked at titanium? And then sort of a more sort of subtext question is spongy form actually transportable easily? Do you need special transportation for it, et cetera, et cetera?
Yeah, it's a good question. So you do have some traders look at titanium metal, but because it is still an opaque market and a contract market, there's less of that in there. But if you could open up that market, you definitely would have more traders look at it. If you could lower the cost of titanium metal and make it more sustainable as well, you would have a much larger market and you'll have the traders want to participate in it. You could trade titanium metal sponge, and you can. It's easily transportable. It's easy to sort of verify and qualify the material when it comes in. But the idea is you want to try and upend that supply chain to move away from the sponge. If you could produce titanium metal in a form which is easily transportable but also easy to take it from a form and make into any component part, you also lower the cost of that supply chain and make it more widely used. Like, electric vehicles and the increased demand of electric vehicles was what made the lithium industry expand. And, I remember when I started Piedmont Lithium, for instance, in 2016, nobody really cared about lithium. People were telling me, it's crazy. Why would you want to build a North American company for lithium? It's all going to be done in China. And there's just, there's not much electric vehicles around. And you could see it coming. And, today you've got a $2 billion company that people now say, well, of course that was obvious. It wasn't obvious back then. I think here you've got, with titanium metal, you've got something which is much more well understood from a downstream perspective on it's a superior metal. If we could get it cheaper, we would definitely want it cheaper. So I think you could rapidly have a lot more interest from the trading groups. But right now, the perception is titanium is so expensive, so it's limited in use.
Yeah.
But if you did bring the cost down, you could have a very large market and very large tradable market, like what you're starting to see evolve with the lithium supply chain.
Yeah. There's also the analogy as well that there is the sort of argument, we had Henry Sanderson talking about his book Volt Rush and Lucas Bednarski on lithium itself, that there's been a certain amount of blind eye turn towards the environmental degradation impacts in manufacturing lithium, as well as the carbon intensity. To heat up these lithium hydroxide plants to 1,000 degrees C, you're using a lot of coal in China. Mm-hmm. There is that opacity there, which is analogous to titanium. I guess the point you're making, though, is that if titanium were cheaper, set aside the carbon intensity and the environmental impacts of titanium manufacturing, if it were just simply cheaper, its inherent utility means it would be much more widespread in industrial applications.
Absolutely, because it is in every engineer's playbook. Unlike lithium, people are still understanding, and people still are understanding the battery, as you would know. So you're still, and people are figuring out, do I use hydroxide? Do I use carbonate? What sort of chemistries are going to prevail on the cathode side? Those questions aren't there for for titanium. Sorry, titanium is well known. Titanium is well understood from a properties perspective. Yeah. You hit grade 5 titanium, you can use it in this application. It's in the software, the structural engineering software where, okay, I'll punch in titanium into that manufacturing of that bridge and I'll punch in this cost. Okay, yeah, I can use it here. It's less of a, although me coming from having founded a very large lithium company, I can see how it's grown. But if you look at the world of metals in general, every structural engineer would know of steel and would know of titanium. They just discount titanium because they're like, well, I can never use that in a bridge because it's too expensive. So there is that utility already inbuilt in people's understanding. Your average civil engineer, structural engineer, or automotive engineer knows the inherent properties of titanium, and there's no sell on that.
Yeah, I mean, they would rather make their car out of titanium if they could.
Absolutely. SpaceX would love to use titanium metal if they could to lower the weight of their spaceships. Absolutely.
Yeah.
Suspension systems, all that. It just doesn't happen because it's expensive.
It's $70,000 a ton. Right. Okay. Yeah. So this is where IperionX comes in, because you've got this. It is a fascinating setup, isn't it? And it's amazing that actually not more effort has gone into lowering the cost, and obviously now the twin imperatives is not only cost but also the environmental impact, given it's such a useful metal. But it has, to date, it is, as you've described, an incredibly not only carbon intensive, but also pretty perilous process to get it to its final form. And it is being done by geopolitical rivals, if you look at it from the perspective of Europe and the US. So I guess this is where what you're doing with IperionX comes in, right? Absolutely.
Titanium metal and the titanium manufacturing process, there's since even William Kroll himself, he was like, well, this is such a terrible process, somebody's going to find a better way, but for now, let's do this. And fast forward 70 years, we're still using the Kroll process to produce sponge and then go through an ingot manufacturing process. Now, there have been groups that have looked at that upstream process, the Kroll process, and trying to improve it, tried to make it less costly, more continuous, but fundamentally not changing the science. Still use the titanium tetrachloride approach and just try, instead of making a big sponge, make powder directly from it. And there was a lot of money that went into it. For various reasons, it did not work, and it really wasn't fundamentally changing the science as well. Then there was the other route, which was the electrochemical route. People were saying, well, this same issue of oxide, of picking up oxygen, was prevalent in the aluminum industry. Alumina is aluminum oxide. And so they were thinking, well, can the electrochemical approach solve this issue? Like it did, like the whole Haru process solved the issue for the aluminum industry and made aluminum cheap, and now we wrap our sandwiches in it when Napoleon used to serve his guests with aluminum utensils. But again, for various reasons, that didn't work, mainly because the affinity for oxygen is far higher with titanium. And titanium as a metal can actually contain up to 14% by weight oxygen. So you could have titanium as a solid block of metal, but it's got so much oxygen in it that it's brittle and it's useless. But when it comes to an electrochemical approach, you can't. Once it becomes that metal, it just becomes so tough to continue to extract those oxygen atoms out of there. So there has been approaches, and there was a lot, but there wasn't a fundamental change in the science, the understanding of how to refine titanium minerals or titanium with high oxygen into low oxygen usable titanium metal. So this is where Dr. Fung came in. Instead of trying to improve the Kroll process or use an electrochemical process, Dr. Fung was a very well-known metallurgist. He's professor of metallurgical engineering here at the University of Utah, where I am today. And 10 years ago, he started, or almost 12 years ago now, he started researching into titanium metal. He was researching titanium or metal hydrides. And I think he had a look at it, and he saw something in the using hydrogen to be able to help to refine titanium metal. So he was funded by the Department of Energy's ARPA-E program. They were looking for a lower cost alternative to making titanium metal to then use it in vehicles for weight reduction and for energy efficiency as a result. And so they funded him, and what happened is that he discovered something that others didn't see in the science. He had a true scientific discovery, but he would say it was always there, but people didn't know this would happen. And what he saw was that titanium oxygen bond, which was almost impossible to break to allow you to reduce titanium oxides into titanium metal, was actually destabilized a little bit by introducing hydrogen into that titanium oxygen, what they call solid solution. So you would introduce hydrogen into the titanium oxide, which is a very common thing to do to create titanium hydrides. And that oxygen atom would break slightly, that oxygen bond would break slightly with the titanium. And all of a sudden, you could then use a very simple reducing process, and in our case, we use magnesium, to then suck that atom off the titanium oxygen, to suck that oxygen atom off the titanium, create magnesium oxide, and you're left with a purified titanium atom. And we can do that in a way where from the get-go, we create a titanium metal powder. Now, we can do that oxygen, that reduction of that oxygen, if the titanium's in a titanium mineral form or if it's in a titanium scrap form. Titanium scrap becomes unusable when it picks up too much oxygen whenever it's exposed to air. So titanium scrap grindings, chips, all that, they pick up oxygen, they become unusable, and essentially they go to landfill or go to the steel industry. So we can do that sucking or that capturing, reducing of that oxygen atom in any form.
Sorry, does that, just so I understand, you're obviously adding the magnesium, but not in the molten form, which sounds much less dangerous. Yes. And much less energetic from requirements. Are you skipping the whole spongiform chloride piece as well?
You're completely skipping chloride, you're completely skipping sponge, you're completely skipping having to melt it in a big ingot, and you're going straight to a powder. And from a powder, it's sort of like making bread, but then from a powder, you can go into any form you want. So if you want a big long bar, you just set up like a die of a big bar, and you fill that powder with bar, and you then sinter. You don't melt. If you want wire, you create a rod, and then you draw it, and you skip 20 steps down to a few steps. If you want a plate, you just fill a big plate, and that's it. If you want an ingot, you fill a big ingot, and you make an ingot if you want it. But importantly, you can go you can go more towards a direct or near net shape process. So if you can imagine, you can go near net shape for an airframe, for instance. You can go near net shape for a lot of products. But especially today with the way the additive manufacturing industry is going, you can take those powders and you can go straight into laser powder bed fusion, binder jet printing. You can go into some advanced manufacturing applications like metal injection molding and create very near net shape products for consumer electronics, for anything, for the automotive industry, for anything. And all of a sudden you've skipped all those steps, so you don't have that huge waste, you don't have the carbon intensity, you don't have the energy intensity. So you've got a product, an end titanium metal product, which is far cheaper, but also far more sustainable.
So two questions. One is, can you give us some sense of scale about how much cheap? I mean, it sounds quite miraculous, right? But can you give us some sense of scale, which automatically, having number of organizations, the number of stories that sort of, I guess, I get approached about, which is we found this chemical process that's going to make hydrogen free and green, right? There's a certain skepticism that, and it always starts with the professor. So just to push back a little bit. But, so can you give us some sense of sort of the scale of the savings? And also, are you seeing, is this something that, is defensible from an IP standpoint, or are we already seeing Chinese manufacturers trying to get hold of this technology? What's sort of that state?
Yeah, it's a good question. To answer the last one first, this was the first papers on this was in 2016, and the pilot facility was built via Department of Energy funding over the last few years, and we only took it over we've only secured the technology in the last few years. So it hasn't been around for long. It's fully defensible. We've got a range of patents over it already that Dr. Fong has. But especially in the last year and a half, we've industrialized our pilot facility. So really in the last few months, we've started manufacturing a lot of titanium metal powder. So definitely defensible. We've got some of the best IP attorneys working with us, and we are extending those patents into a range of other applications, process patents, and just improving our patent portfolio, but we're also keeping some things trade secret. Can people steal it? It will be hard. We have got patents in China, but it will be hard for others to come in and do what we're doing. There's a lot of trade secrets in this as well. And we continue to improve and optimize. But it is a very young technology still, but we are already seeing massive savings in some of the products, a lot of which I can't talk about because we've yet to publicly announce, some defense, but some also in the automotive and consumer electronics section. But we have got a public announcement out there in the luxury goods sector which uses titanium metal in watch cases, for instance. But if we look just from a very high level in terms of savings, if you look at directly to sponge, and you looked at this as just a sponge replacement, which is the wrong way to look at it, but if you just look at the energy reduction of just getting to the primary raw metal, you're looking at a 50% energy reduction. So already there, 50% less energy, a lot less cost. But then you layer on top of that, it's a much more simple process, much more scalable. You have significantly cheaper opportunity here to manufacture that titanium metal. Now, it depends on how far down the supply chain you want to go. If you go directly from our powders to parts, you're going to have massive reduction It really depends on the parts. But if we look at powder, so the supply chain for 3D printable powders for the 3D printing additive manufacturing market, today titanium metal powders sell for about $250 a kilo. We believe, and we've publicly announced, that we can get a 75% reduction in that cost. And I believe we can even go further as we optimize and scale this process. And this is something that we don't need to build $1 billion facility to do. We will do it on a facility which we're building today in Virginia for around $20 million. So it's not a technology where people say, look, this is amazing, I need $1 billion to prove it. Like a lot of these geothermal brines in the lithium industry, for instance, this is like, this is a very scalable process that we can very quickly show that we can lower the cost. And so that is what we're embarking on in the next year. We're already showing people with the products we're producing today, but you're talking about a significant order of magnitude cheaper. And just to give you an example, in the 3D printing industry, a reference point, in the 3D printing industry, spherical titanium metal powders are around $250 a kilo plus, but aluminum alloy powders are around $100 a kilo, and you're buying stainless steel powders for $40 to $50 a kilo. So if we can more than halve the cost, we're already at the cost equivalency to those metals in that industry. That gives you a sense of the sort of cost reduction you can achieve with this technology.
Yeah. So you mentioned aluminum, right? There's that very descriptive idea that it was so expensive to manufacture, and now we're wrapping our sandwiches in it. I mean, do you see, perhaps taking it outside of IperionX, but is there ongoing intensive work, given how useful titanium is, to lower the cost so that we do get to a stage where it can be widespread and critical to energy transition in that weight reduction, and also, obviously where everyone wants to go on from a space travel standpoint, it's going to play a key role in that. I mean, do you see a bright future for titanium in these efforts to tackle it, or is it at the moment, outside of what you're doing, quite moribund in the sense that it is so energy intensive, it's so environmentally impacting that it just is, outside of those critical uses in the defense industry, it's going to stay where it is unless, a breakthrough like this works?
It's more reliant on our breakthrough now that, if the industry knows about access to lower cost titanium metal products, you're going to instigate the industry to get back on and want to use it. There was quite a bit of work go into titanium metal powder as a way to, even though it's the raw mineral form, to get it into an ingot. They realized that, a lot of the cost of a titanium metal part in the end, some of it is that refining cost, but half of it is the post-processing cost to get it into a part. So there was a lot of work go in there to reduce that. So we can piggyback off that, but it's sort of, in the last few years, people have given up and said, it's always going to be expensive. Let's try and at least reduce the waste along the way as a way to lower the cost of titanium metal products. So we're piggybacking off the back of that. But the auto industry, the aerospace industry, the defense industry has looked towards applications in high-end, and even the consumer electronics industry has looked at high-end products that we can piggyback off as well. Using titanium, for instance, in consumer electronics, because it's a better metal. And having it in the premium products. You see the Apple Ultra, for instance, the Apple Watch Ultra is a titanium case. You see Porsche, for instance, and Bugatti and all that using titanium metal brake calipers and titanium metal components across their premium vehicles. So there is already products there that, quite frankly, if you're cheaper, those products would be far cheaper, and all of a sudden you'll use it in the, in a range of, higher end luxury vehicles, or you'll use it in a range of more consumer electronics. So it's sort of somewhat already established, that downstream industry for high end products that could easily go in more mainstream if you brought the cost of the powder down. So we are able to piggyback off a lot of that, but I think what you'll see is, for instance, in the maritime industry, we've had publicly disclosed project going on with the US Navy, and essentially we're looking at lowering the cost of titanium metal products for them and recycling of titanium metal products for them. But there's use of titanium metal pumps in the Navy extensively because of its corrosion resistance and its lighter weight. but it's not used in the commercial industry a lot because of the expense. The Navy, you have a submarine or a ship out there, you don't want to have to bring it back to dry dock. You want to keep it out there if there's a war.
Yeah, and you've got a bottomless wallet as well, so that helps.
Exactly, you've got a bottomless wallet. So they use titanium. They use titanium to keep the ships out there, the ballast pumps and all that. They want to keep the ship out there. If they stay out there for years, it doesn't need to come back. Whereas we use stainless steels and stuff in our pumps today in industry. Well, if you brought the cost down, all of a sudden we think there's a huge opportunity for marine chemical industries, where it was always stainless steel because that's the cheaper option, where if titanium was cost equivalency, you would never replace those pumps, so you'll go titanium. So I think there is some downstream industries already built for the higher end products of those industries, which it can very easily fit into those higher end products using our powders, using powder metallurgy or 3D printing. But then I do think there's this wider idea of, well, if titanium's going to be cheaper, could we start using it in other consumer products? Could you see you see stainless steel, extensive use of stainless steel in kitchens, well, why couldn't you use titanium instead for a lot of those products? I think we will instigate a revolution in the type of metals we can use, and all of a sudden, because of our process, we can also have 100% recyclability, but we have that carbon intensity, which is far less than stainless steel and aluminum, and that traceability, where we can produce it all from a far more traceable, sustainable supply chain from the ground up, creating a fully traceable, fully sustainable, fully circular supply chain. And all of a sudden you go, well, why should I use stainless steel where the nickel's coming from Russia, and I don't know where that's coming from, and we should be using the nickel in electric vehicles anyway. Why should I use aluminum when that alumina is coming from very dirty operations, from bauxite to alumina, which are creating these toxic red mud piles? Why shouldn't I use more titanium metal in a lot more of our products? And that's where I see the industry going. We can produce a superior metal that also has the advantage of being sustainable at cost equivalency. And it's the sort of holy grail of everything, especially in today's world. It's a better metal, but you're not having to give up on sustainability or cost. It's a better metal at a reasonable cost with superior sustainability attributes.
Well, I think I've learned two things. One is why Lieutenant Dan was so proud of his titanium leg, the same materials they use in the space shuttle, because it was obviously very expensive and much lighter for him to use. And I think it is. Well, it's fascinating how the world of titanium, how it really only exists in these special purpose applications because it is so expensive, and also the analogy to some of the other critical metals and how the processes to produce these metals is so energy intensive, so environmentally destructive that it has impacts often which are hidden, we have to say. And I wish you guys the best, because I think it sounds like a worthy project. So we'll put a link to IperionX in the show notes so people can come and check it out. And I guess we'll all be watching this story and for the sake of lots of things, hoping it works out.
Absolutely. I really appreciate it. It's been great, and I don't think people are going to have to wait long. We've got some things in the works right now, and I think the next 12 to 18 months is going to be amazing for us and for what we're doing.
Thank you for listening. If you enjoyed this episode and want to support the show, please give us a positive review on Apple Podcasts or Spotify.
To find out more about HC Insider and HC Group, a search and advisory firm dedicated to the commodity markets, visit our website at www.hcgroup.global. There you can find out more about our services and our offices around the world. There you can also find more content, from interviews to insight pieces to more podcasts focused on the commodity value chains. Thanks again for listening.